So let's look at now how to solve differential equations. So let's look at first order differential equations. D is linear and non-linear. So all the methods that are used to solve linear and non-linear first order differential equations, so those will be described here. So basically we'll study four methods here. Let me list out those methods. First is the variable separation method. Well, if so, we'll see how the general form of the differential equation should be in order to apply each of the methods. And then the homogeneous equation method. The third is your linear equation. So this gets applied only when you have a linear equation. And fourth is the exact equation method. So these are all so basically four methods. So we'll see how each of this, and there will be a small variation, a small combination of each of this method, extension of each of this method. So we'll see all that. So first let's begin with the thing. So most of the first order differential equations are of this form. dy by dx is equal to f of x comma y. So this is the general form. I mean, you can bring most of the first order d's in this form. Okay. So now let's see how the first method, which is variable separation method. So what this method tells us is that the idea is basically to separate all the dependent variables and the independent variables on separate, and one side, so that you have one side all the dependent variables and the other independent variables on the other side. And then what? Then basically integration. So let me just write down the idea. The idea is to separate all the dependent variable related terms. Dependent variable means it, I mean, mostly it is y or the unknown function terms. So all the dependent variable terms, if you are able to bring on one side, and all independent. So looking at the differential equation, you have to just see which method I can use, and so every method has some or the other requirement. Like for example, this variable separation method has this requirement: if you are able to separate, then it is well and good. Otherwise, basically you cannot apply this method. And then use integration on both sides. Okay, so fairly simple. Okay, so generally it's like this. Let me just describe this method. If you have dy by dx, if you can bring in this form, if you can just separate it such that it looks like this: f of x into g of y, some functions of f of x and some functions of g of y, then I can just bring the dependent variable, which is y related terms, on one side and the x related terms on the other side, and then basically integrate on both sides. So integration should be performed as many times as the order of the, yeah, order of the differential equation. So that again depends on finding, expressing the differential equation, and I mean getting the order and then integrating it such that you get required number of arbitrary constants which are equal to your order. Okay, so this is a fairly simple method. Let's take two examples now to demonstrate this method. The example one is that if dy by dx is equal to x by y, so solve the dy by dx is equal to x by y. So if it's not visible correctly, let me write down x by y. Okay, so what I'll do is I'll just try to bring the y terms together one side. So a simple can do. Now just try to integrate. So when I integrate on both sides, I can write in this way. So integral y dy is equal to integral x dx. Okay, so this is basically y square by 2, and this is x square by 2 plus some constant term. So constant terms I'm just writing here. So this becomes y square minus x square is equal to 2c, and 2c is again big constant, so I'm just writing c1. You just write c1 y square minus x square. Okay, so this is your general equation, or these are basically the family of curves which satisfy that differential equation. So let me just plot this. I mean, just for curiosity's sake, if I plot this, remember I don't have any, I don't have any boundary condition, so I cannot apply boundary condition to find out C. Just plotting this based on the values of C. So if C, say let's take C is uh, 1, C is 0. Yeah, if C is 0, this basically becomes y is equal to plus or minus x. So that is nothing but a straight line, right? So these are for C is equal to 0. Okay, C is equal to 0, you have this straight line. Okay, similarly for C is equal to 1, this becomes x square plus 1, and when you just solve it, so you just plot it, it looks something like this. This is for C is equal to 1. Basically for C is equal to 1, you will have, this is symmetric, right? Symmetric about x and y. So if you substitute C1, basically C1 is equal to 1. So you will have curves, two set of curves on the both sides. Similarly, this is C is equal to 2, or C is equal to 4, and C is equal to 9. So these are general family of curves. Okay, all this is C is equal to 1. So these are all C is equal to 0 lines, or straight lines are basically C is equal to 0. And for C is equal to 1 and C is equal to 2, it is basically a parabola, you can say, some kind of curves. Okay, C is equal to 1, C is equal to 4, and C is equal to 9. Well, if I put negative values, then I'll be getting, if I put negative values, say C is negative, then y is equal to h square plus c, and then when you try to plot it, it looks something like this. Okay, so this is c is equal to minus 1, this is c is equal to minus 4, and this is c is equal to, so this is then again symmetric about y-axis. Okay, the negative. So this, the idea is, when you plot the general family of curves based on giving different values to the arbitrary constants c1, you get a family of curves. Get family of curves. Okay, so all these curves, that is straight lines for c is equal to 0, and curves for c is equal to 1, 4, 9, all for all the values of c, will basically satisfy the differential equation. Now based on the boundary condition, or based on the initial value thing for x or y, I mean the boundary condition, you can zero in on to the required curve, the required solution, that will become the required solution. But in general, this family of curves given by y square minus x square is equal to c satisfies the given differential equation. So it means that all this family of curves satisfy the differential equation. Okay, so I mean, you need not every time draw this, but just to get the feel what happens when you solve the solution and what happens when you put different values to the arbitrary constants. Okay, so this is, I mean, this is basically you can say a family of rectangular hyperbolas. Okay, so this is the general equation for the hyperbola: y square minus x square is equal to c. Okay, okay, so now let's see another example based on this the same thing, extending this. Okay, so here solve the initial value problem dy by dx is equal to x square y cube and y of 1 is equal to 3. So this is the initial value problem and we are supposed to solve this. So here basically there is another, there is at x equal to 1 y is 3. So they have given some initial value that at x equal to 1 y takes the value of 3, basically to eliminate the arbitrary constant. So let's take the differential equation and let's see whether we can bring all the y terms on one side. So y cube can be brought this side and x square is on the other side. Now if I integrate 1 by y cube, this becomes the form of, so let me just tell you something. When you are integrating xn dx, it becomes xn plus 1 by n plus 1. So similarly here you have y to the power of minus 3. When you integrate, it will be y minus 3 plus 1 by minus 3 plus 1. It will be minus half y square, because this is y power minus 2 minus half. So this will be minus half y square, and this x square, this going in the same form, same formula, integration formula, it is x cube by 3 plus some constant. Okay, some constant. So if I now want to rearrange this, okay, now let's first just find out the constant value. So at x equal to 1 y is equal to 3 implies minus half 2 into 9 is equal to 1 by 3 plus c. So if you just simplify this, c will come out to be minus 7 by 8. You can just calculate from this, c will come out to be minus 7 by 8. No, it's minus 7 by 18. You can just let me just simplify. Minus 1 by 18 minus 1 by 3, that comes out to be minus 21 by 3 into 18, which is 7 by 18. So c comes out to minus 7 by 18. Let's substitute it back in the differential equation. Okay, so substituting it back in the given equation, I can express the the equation after keeping the x value something like this. Just on simplifying, you will get this. So note this, this is the solution of the initial value problem, whatever was given. And remember that it is valid only for 7 minus x cube greater than 0. Okay, so from this you can get that x cube should be less than 7 by 6 and x should be less than 7 by 6 whole power 1 by 3. So this is the solution which is valid for this. Okay, so sometimes you have to always check, like for what domain or what values of x, what values of independent variable the solution is valid. Okay, you can't say that this is valid for all, because otherwise the denominator, the root, inside the root, it may become negative and stuff like that. Okay, so this was all about the variable separation method, and we just took very simple two examples and tried to separate it. Okay, so now let's move on to the method 2, which is homogeneous equation method. Okay, so homogeneous equation method. So what does it say? So it says that if you can have a differential equation in this form, dy by dx is equal to, say, something like this. You have just expressed numerator and denominator as some functions of x and y. Now what it says is, if uh, if the degree of each of the term in f x comma y and g x comma y is same, then you say basically it's a homogeneous in that sense. So in that sense, if the degree is same, then I can always, the degree is same, then it is possible to express this f of x comma y and g of x comma y together as some function of, so let me call, I have used f and g, so some function of y by x. So this happens only when each of the term in f of xy and g of xy is same, the degree is same. So that's why the term, that's why it is used as homogeneous. If the degree is same, it becomes a homogeneous equation. Okay, and that this equation is called homogeneous. Okay, so this is the primary requirement for this method. Okay, so don't confuse this homogeneous with what we studied at the class during the classification of differential equation. There the homogeneous was if you can express it in a polynomial form, okay, a linear differential equation, linear ODE, then if right hand side f of x is 0, it becomes a homogeneous differential equation. But this homogeneous has nothing to do with that. This is just looking at f of x, f by g, and if you can bring entire thing in y by x form, and that you can bring only when the degree of each of the term is same. Okay, so we'll see some examples. So okay, if what happens if this is satisfied, if this is satisfied, then what he says is put y by x as v, so I can write y is equal to vh. Now if you differentiate with x on both sides, and so v is just a function of x. Remember, y by x as v, v is some function of x. So if I apply the chain rule, I can write dy by dx into, into x and chain rule plus v into dx by dx, which is 1. So I can write x dv by dx plus 1. So this is the expression for dy by dx. So now try to substitute, try to bring substitute y and dy by dx in terms of v and x, in terms of v and x. So now then you can use the, that's the entire d will be in v and x, and then you can use the variable separation method, okay. So this is all about bringing the required equation in the v and x, and then use the variable separation method. Okay, okay, so let's take some examples in order to describe this. Okay, so let's solve one example describing the method of homogeneous differential equation. So it says that dy by dx is x square plus xy by xy plus y square. Okay, so note that each term each term in numerator and denominator on the right side in this and the this is of degree 2, each term, right? You can just easily see that. Okay, so basically this is a homogeneous equation, homogeneous in that sense, homogeneous equation. And so yeah, you can try to bring in y by its form, try to bring in y by x form. Okay, so let's see that how to bring in x y by x form. So if I just try to take x square common from both numerator, I can write y by x, right? And this also, if I take x square common, I can write y by x plus y square by x square. Okay, so this can be written 1 plus y by x by y by x plus y square by x square. Okay, now as the method says, put y is equal to vx, and dv by dx will be your dv by dx into x plus v into 1. Okay, so this is what I'll substitute back this 1 and 2 in. So this 1 and 2 substituting back, so what we'll get, so dv by dx I can just replace it as v plus dv by dx into x. Okay, and y by x I can directly replace by v, so v plus v square. Okay, so entire thing you're able to bring in terms of v and x. Okay, so just simplifying 1 plus v, I can remove v common here, so it will be 1 plus v here, and here also, so this will be 1 by v plus dv by dx into x. Okay, and so just simplifying further is 1 by v minus v, and that is nothing but just bringing entire thing 1 minus v square by v into x dv by dx. So this I can now try to bring in the separate in the variable separate form. So all the v terms on one side, remember v is y by x, so that we need to substitute later, and dx by x. So this is all. So this looks in a variable separation form. You can just easily apply variable separation form. Okay, so now if I now the derivative of 1 by v square, 1 minus v square is minus 2v, and we have v on the other side, so just we need to multiply with the constant. So here need to, we can integrate on both sides. Integrating on the both sides, we have something like this. So let's do it this way. Okay, so in order to make integration easy, let's put u is equal to 1 minus v square. Method of substitution in integration is quite common, and this becomes du as minus 2v dv. So substituting all that back, so v dv can be written as minus half into du by u integral dx by x. So integral du by u is basically ln u or log u. So let me write ln u. Remember that u has to be positive here because it's inside log, and here it is ln x plus the integrating constant, which is c. So now, so I can write minus 2 I can take on the other side, or let's take 2 on the other side. So minus ln u is 2 ln x plus 2c. Well, 2c can become another constant c1. Okay, you can write this as ln x square because you have a general property 2 into ln x plus this. I can, the entire constants I can replace with some other ln of another constant, ln c1 let's say, and this is ln u minus. So minus I can take, it will become ln u ln x square plus ln c1. Okay, and these two together I can write ln h square c1 ln 1 by u. So just equating all the ln terms, I'll get 1 by u is equal to h square c1, h square into c1 some constant. Finally you can just replace it with c1 as one constant, some, okay, c1 as with another constant c2. Okay, so u is, again now substituting it back, u is 1 minus v square, and v was and v was what? V was your 1 minus y by h whole square is equal to h square c. So just taking the reciprocal, you will get 1 minus y square by h square is equal to 1 by h square into c, and the 1 by c you can just write another constant c naught by h squared. So finally your equation is something like this. Okay, this is your required equation. So you can actually, I mean, if you want, you can just put mod here because u has to be positive here, and x square it becomes positive. So mod u you can keep, because ln 1 by u du integration has to be mod, because inside ln you can't have. So this is mod, and this is entire thing is mod. So this is mod. So just to say that only the absolute value of this 1 minus y square by h square has to be equal to c naught by h square. Okay, so mod is there, the absolute value. Okay, so whenever, just remember that whenever you're taking integration and it is 1 by u, I mean it's something like this, integral dx by dx, it should be ln mod x. Okay, because x inside log you can't have negative values, so that's the thing. Okay, don't put ln x. Even if you put ln x, it means that that thing is valid only for x equal to greater than 0. So now this thing is valid for all x values of x. Okay, so this is how you solve something by homogeneous method. So let me put this as integration by substitution. Okay, so this was one example which describes how an homogeneous equation, differential equation, can be solved. So now let's see equations which can be reducible to homogeneous form. Okay, homogeneous form. So if you have, say, dy by dx as a1x plus b1y plus c1 is equal to a2x plus b2y plus c2. So here you have let's two cases here. Cases one, when a1 by a2 is equal to b1 by b2. So when you have something like this, a1 by a2 is equal to b1 by a2 and is equal to some constant k. So then you can write a2x plus b2y as some k times of a1x plus b1y, right? This can be written when you have a1 by a2 is equal to b1 by b2 is equal to k, you can always write. And now keep a1x plus b1y as v. That's what this method says. Okay, and then try to just bring entire thing in variable separation form. So when you keep this expression, okay, and now if you just solve it, like if you just, so this, now if you just differentiate this equation, a1 plus b1 dy by dx is equal to dv by dx. Okay, so now substitute all this in the main equation. So the main equation dy by dx, this is v plus c1 by kv plus c2, and dy by dx you can always substitute from this. Okay, so it will be basically dy by dx minus a1 by b1 is equal to v plus c1 by kv plus c2. So now use variable separation method. So always the basic idea is to bring in the variable separation form. Okay, that is the idea behind the homogeneous equation. So if something is not homogeneous, you have to try to bring it into homogeneous. So that's what this equation, we reduced it to the homogeneous form. Okay, now another case, when you have a1 by a2 not equal to b1 by b2. So in that case, what will you do? So in that case, we basically offset the variables, like x, small x equal to capital X plus h, and small y is equal to capital Y plus k. So basically we substitute x and y with, we are substituting x and y, replacing x and y with new variables capital X and capital Y and h, such that h and k are constants. Now what are h and k? Now that is another question. So that's what we do is we choose constants h and k such that the constant term in the numerator and denominator becomes 0. In the numerator, I am writing in the short form, and denominator becomes 0. So two terms and therefore two equations for knowing h and k. So once you get h and k, then you have to just bring in the, and then it becomes a homogeneous case, right? Then it becomes a homogeneous case, because see, when you have only x and y, then you can always, when you don't have constant terms basically in the numerator and denominator, it becomes homogeneous, and now the method is same, homogeneous. So rest of the method is same. So let's take one example to describe this case. So let's take an example in describing this homogeneous method. So dy by dx is equal to y plus x minus 2 by y minus x minus 4. So this I can write putting x terms first. X plus y minus 2 is equal to minus x plus y minus 4. So clearly 1 a1 by a2, which is 1 by minus 1, is equal to minus 1, and b1 by b2, which is 1 by 1, which is 1. So a1 by a2 is not equal to b1 by b2. Okay, so now we have to assume that x is capital H plus h, y is capital Y plus k, and now substituting in the numerator term will be h plus h plus y plus k minus 2, and therefore the constant terms will be h plus y plus h plus k minus 2. H plus k minus 2 is the one term. Now in the denominator you will have minus h, so minus h plus h plus y plus k minus 4 is equal to minus h plus y and minus h plus k minus 4. Okay, so all the constant terms I have to set it to 0 in order to find h and k equal to 0. So from this, solving these two, I get h is equal to minus 1 and k is equal to, you can just add two equations, so directly you will get k is equal to 3, and substituting back you will get h is equal to minus 1. So that's the thing. And now so what will happen to the our equation? Okay, so x is y. So now what does this means is that small dx is capital Dx and small y is capital Dy. So basically dy by dx is basically capital Dy by capital X. So all that, now let's substitute in the star equation. So you will have capital Dy by capital X is equal to the constant terms have become 0, so it will be x plus y by x minus x plus y. So this is a homogeneous equation in x and y. Capital X and capital Y. See, remember, ultimately you have to substitute in small x and small y. So now same thing, I'll just employ the homogeneous method where y is equal to v by x, and therefore d capital, all these are capital now, is equal to v plus v into x ka derivative 1, and then dv by dx into x. Okay, this you need to just substitute back. So now if I substitute all that in this equation, so what will I get? V into dv by dx x is equal to, now x if you remove common, you will get 1 plus y by x by minus 1 plus y by x, which you can write 1 plus v by 1 minus 1 plus v. Okay, and now trying to bring in the variable separation form, 1 plus v by v minus 1 minus v. So this I can always write in this way. Just if I simplify, I'll get something like this. Okay, and now keeping it in the variable separation form, I can write v minus 1 y 1 plus 2v minus v square into dv is equal to dx by x. Just integrating on both sides. So now integrating on both sides, one thing is, if you look at the derivative of the denominator, this term is what? 2 minus 2v, and we almost have that. This can be written as minus 2. If you take out a common, you can write v minus 1, and v minus 1 is there in the numerator. So you just multiply. So what I am doing is, I can write minus half here and multiplying 2. So basically minus half here, and I can write minus 2 there. So minus 2 v minus 1 by 1 plus 2v. So it doesn't make difference. What you have done is, you have divided by minus 2 and multiplied with minus 2. Okay, so no harm to the equation. And so now if I integrate, okay, so what, log 1 plus 2y by x minus y by x, y square by x square is equal to, I can write log x square minus and minus c. Log minus, it will become here plus, so log 1 plus 2y by x minus y square minus x square plus log x square is equal to c, and this I can write log a plus log b is log ab. So 1 plus 2y by x minus y square by x square into x square is equal to c. And c, well, c is negative here. Okay, so minus c you can put, and therefore it is log. So now if you just take, we just multiply here x square, so log x square plus 2xy minus y square is equal to minus c. Take exponential on both sides, e power minus c you are getting. Actually there should be 2 here, because 2 gets multiplied and the constants 2c. So 2c is basically another constant you're writing. So let me write e power minus 2c, and now is the time to substitute it back. So e power minus 2 is c, some big bala constant, and now put x, I'll be substituting x minus h, and y as y minus k, which we got small x, h as minus 1, so, and k as minus 3. So substituting back, we'll be getting x plus 1 whole square in the place of capital X, and in the place of y it is capital Y, it is y minus 3 minus y minus 3 whole square is equal to constant. So this is your equation, the solution for the equation dy by dx is equal to y plus x minus 2 by y minus x. So this is how you can reduce the equations to homogeneous form if it is not homogeneous, and once it is homogeneous you have to substitute y is equal to y by x as some v. Okay, so that's the idea. So let's move on to other method. This was the idea. I mean, we have seen two methods till now. One was the variable separation method, and the second is the homogeneous method. And homogeneous, if it is direct, you have to just check the degree of each term. If it is direct, you have to just put y is equal to vx, and the dy by dx also in terms of v and x, and then you have to get in the variable separation form. If the equation, if you have constant terms, then if the ratios are equal, a1 by a2 is equal to b1 by b2, then you can just put a2x plus b2y as some constant of v times, or some, I mean, you can express a2x plus b2y as some k times the numerator a1x plus b1y, and putting a1x plus b1y as v, you can bring the entire form in a variable separation form. The second case is a more general case where a1 by a2 is not equal to b1 by b2. In that case, what you have to do is you have to remove the constant. So what you have to do is you have to just substitute small x and small y with the new variables capital X and capital Y offset by some constant. So small x is capital X plus h, small y is capital Y by k. So you have to substitute it back, and you are free to choose h and k. So bring h and choose such that the constants in each term, the numerator and denominator becomes 0. So for that you will get two values of h and k, and so that was the idea. Once you remove the constant, now the entire equation becomes a homogeneous equation capital X and capital Y. So remember, the small dx is capital Dx and small dy is capital Dy, because h and k are constants. So once you bring in this in the homogeneous form, then it's simple. It's just variable separation method. So let's move on to the third method.